focusing on the two-round publicly verifiable setting in which we have a prover and a verifier that satisfy some notion of, the standard notions of completeness and soundness. And the prover wants to prove the membership of X in some NP language L to the verifier. And here what we mean by publicly verifiable is that anyone who trusts the verifier can use the first round message to verify the second round message. And this is implied trivially by any public coin protocol, in which we mean that the verifier's first round message are just random coins. And the reason why we care about public verifiability is that this typically allows the first message to be reused for multiple proofs. And the question we ask in this setting is, what kind of security can we guarantee against a malicious verifier who's attempting to extract some information about the witness? So in the general cryptographic proof system setting, we know that from Goldreich, Oren, Barak, Lindell, and Vadan, that to obtain our standard notion of the next button's not working? Maybe I just have to press harder. OK. So in the two-round publicly verifiable setting, what kind of security guarantees can we obtain? We can obtain witness indistinguishability, which says that the verifier can't tell which of two witnesses the prover used to produce the proof pi. Witness hiding, which says that the verifier is unable to extract out an entire witness from the proof. And superpolynomial simulation, which is a variant of the standard simulation-based notion of zero knowledge, in which the simulator can run in superpolynomial time. So how should we interpret these security guarantees qualitatively? So let's consider a toy example in which we consider an encrypted signed document with 3 sensitive fields of information. So for example, sensitive 1 could be your social security number, sensitive 2 could be month-by-month financial transactions, and so forth. And just observe that these sensitive attributes have really not much to do with each other. You can't really computationally predict one sensitive attribute from another sensitive attribute. Now, in the case that, for example, this encryption scheme used, it has perfect correctness, then the statement has a unique witness. And witness indistinguishability doesn't really give you a meaningful security guarantee, because a witness indistinguishable protocol for any language with unique witnesses can just give out the entire plaintext. It can give out the entire witness, and that's a valid witness indistinguishable protocol. Witness hiding doesn't prevent partial information loss. For example, it could be that the witness hiding proof leaks out sensitive 2 and sensitive 3, but you're unable to efficiently compute sensitive 1 from attributes sensitive 2 and sensitive 3, so you can't extract out a full witness W, but it still leaks sensitive 2 and sensitive 3. And then superpolynomial simulation roughly says that it leaks information, the proof leaks information, computable in superpolynomial time. But how do you know if sensitive 2 is computable in superpolynomial time? This is something you would have to interpret and argue for. So this is a disadvantage. So the question is, can we have stronger qualitative guarantees than the above 3 security guarantees? And as we said earlier, Goldreich, Oren's classic triviality result and other work by Barak, Lindell, and Vadan show that zero knowledge is impossible in this setting. But as noted by Batansky, Karan, and Paneth in 2019, the Goldreich-Oren triviality result actually extends to even weak zero knowledge, where the quantifiers are reversed and the simulator can depend on both the distinguisher and some epsilon parameter for the advantage. Even weak zero knowledge is impossible in the two-round publicly verifiable setting. So this is rather unsatisfactory that we have this large gap in guarantees between the above 3 notions and weak zero knowledge. And so to address this gap in this work, we introduce a notion called witness semantic security. And we construct a two-round public coin, which is publicly verifiable, cryptographic argument satisfying WSS from the sub-exponential hardness of LWE. So let me explain what witness semantic security is. So let's go back to Goldwasser-Macaulay, 1982. There they defined this notion of encryption semantic security, which we now know is equivalent to ciphertext indistinguishability, but these two are initially separate notions. And encryption semantic security says that information about the message that can be computed given the ciphertext can also be computed without the ciphertext. And analogous to this notion of semantic security, we're going to define witness semantic security to capture the notion that information about the witness that can be computed given the proof can also be computed with only the statement. So intuitively, a witness semantic secure proof should hide all non-trivial information, even partial information, about the witness. So here's a basic variant of the definition that we present in our work. So we're going to consider a distribution over statements, witnesses, auxiliary information, and deterministic functions f. And then we're going to consider some function of the witness y, so y equals f of w. And what we're going to say is that whenever there's a malicious verifier a1, a2 that is able to extract out f of w for the w that the prover used to produce the proof, then there should be an efficient way to extract out this y without ever interacting with the proof or the prover. Okay? And just note that this definition is in the delayed input model in the two-round setting. And here by delayed input model, we mean that the first round verifier message is independent of the statement, both the honest and malicious verifier. And we'll revisit this delayed input model setting as well later. Okay, so at this point you might be asking, is witness semantic security morally like zero knowledge? Okay, so why does this definition not imply some distributional notion of zero knowledge? We're working over some distribution. Okay, and first we observe that, look, the guarantee is that the malicious verifier is unable to extract out f of w for this specific w that the prover uses. So that might be your first objection, why this WSS definition is weaker than zero knowledge. So let's address this. We're going to introduce a notion called verifiable witness semantic secure, and I've highlighted all the differences in red. So a two-round interactive argument system is VWSS. If we consider distribution, which doesn't consider f of w for specific w, and this f needs to now satisfy this verifiable input-output condition, which simply says that if you give me a pair x and y, a statement x and some y, you should be able to efficiently verify that this y is in fact a function of some witness, of any witness, for this statement x. And just note, for example, if f is the identity function, then this definition is immediately witness hiding. But it basically says that, for every if there's a malicious verifier that is able to recover from interacting with the prover a function of any witness of the statement, then there should be a efficient way to do this without interacting with the prover or the proof. Okay. So, okay, now you might be asking, verifiable witness semantic security really looks morally like zero knowledge. So what's different between verifiable witness semantic security and zero knowledge? So here's an observation that's a bit perhaps weird, is that existing simulation-based notions of zero knowledge ensures the hiding of all non-trivial information about the transcript. So perhaps you can't imagine this, nor can I, but perhaps the prover is able to compute something, possibly inefficiently computable by the verifier, about the verifier's first message that the verifier itself does not know. So this is saying, like, the prover is somehow able to show something that the verifier itself does not know about its own message. And the simulation-based notion of zero knowledge says that this is not possible. This is not allowed. Whereas WSS and VWSS actually allows this behavior. The prover is somehow able to use knowledge about the first message that perhaps, even though it's generated by the verifier, that the verifier itself does not know. And we'll actually exploit this to achieve this notion of zero knowledge. Okay. And here's a quick map of how WSS, VWSS relate to WI and WH. So WSS implies WI. It's very straightforward. VWSS also implies WH in a very straightforward way. And these are provably separated. So there are WI protocols that are not WSS, and there are WH protocols which are not VWSS. WI and WH similarly have the same property. There are protocols that are WI that are not WH. There are protocols that are WH that are not WI. And WSS and VWSS are rather incomparable. So you might be rather wondering, okay, if you might be unhappy that WSS and VWSS have nothing to do with each other. But we're going to soon show a security notion that implies both. Okay? So before I do that, I'm going to give you another viewpoint on two-round protocols, which is CRS model non-interactive proof systems. So let's say we start with a two-round protocol between P and V. So beta 1 is the verifier's first message. Alpha 1 is the prover's message. And to get a CRS model, what we're just going to do is move the verifier's first round message into the CRS. So this is a relation. And a key difference between standard two-round protocols and non-interactive zero-knowledge is that in standard two-round protocols, the verifier first gets to see the statement and then produces its message. So the first message is actually statement dependent. Whereas in the NISIC setting, the CRS generator does not see the statement and produces a CRS to be used for subsequent statements. So instead, the correspondence between these two settings corresponds to the delayed input model in the two-round setting, where in the delayed input model in the two-round setting, the verifier's first message is independent of the statement X. Okay, good. And so a natural application is that if I start with a two-round protocol with any ZK property, let's say ZK star, it could be witness indistinguishability, it could be witness hiding, it could be WSS, I actually get the property that when I convert it into a non-interactive zero-knowledge protocol in the CRS setting, that whatever ZK star property is guaranteed in the two-round protocol is still guaranteed even if the malicious verifier is colluding with the CRS generation process. So this has been studied as the subversion CRS setting by Bellare et al. And sometimes we'll just refer to it as the malicious CRS setting. And you might be wondering, isn't soundness more important when the CRS is maliciously generated? But Bellare and al. Show in their Eurocrypt paper that if soundness holds when the CRS is maliciously generated, then you cannot even have zero knowledge against the malicious verifier when the CRS is honestly generated. Okay? So we're going to introduce a new notion of simulation that uses this alternate viewpoint. And this new definition of simulation will actually capture exactly the observation we had for VWSS and WSS. And this new notion of simulation will also imply both of them. So let's review the standard non-interactive zero-knowledge definition. So the standard notion of simulation. Here we have a simulator S1, S2. The simulator gets to pick the CRS. In general, the CRS is trapdoored so that the simulator can prove in the third step proof pi without knowledge of the witness W. And the CRS will be computationally or statistically usually computationally indistinguishable from an honestly generated CRS. Now, our new notion is, we call it non-uniform zero-knowledge with auxiliary input. Now the simulator gets to depend non-uniformly on the CRS. So for every CRS, there exists a simulator S who depends non-uniformly on the CRS, so it can contain even uncomputable information about the CRS, such that the honest proof is indistinguishable from the simulated proof. Okay. So this is our definition. And just recall that VWSS and WSS allows the prover to potentially leak interesting information about the first message, the verifier's first message. And in this case, that's the CRS. And this is exactly captured by the simulator's non-uniform dependence on the CRS. So the simulator knows something about the CRS that even the verifier does not. Okay. So in this work, we start with the sub-exponential hardness of LWE. We construct a malicious uniform random string NUZIC argument. And we compile this into a two-round public coin VWSS argument that also satisfies WSS. So the main theorem is, assuming the sub-exponential hardness of LWE, there exists a two-round public coin, you should ignore ZAP, two-round public coin argument system that satisfies both WSS and VWSS. ZAP usually refers to witness indistinguishability. That's a mistake there. And then the main technical tool is we construct the first ZAP with computational adaptive soundness from the sub-exponential hardness of LWE. Previous works that construct ZAPs from the sub-exponential hardness of LWE have really considered statistical witness indistinguishability, which is in some sense a little incompatible with adaptive soundness. They only get non-adaptive soundness in the works of, I think I'll cite it on the next page. But in any case, this main technical tool requires the existence of what we call a super dense PKE from LWE, which may be of interest for independent constructions. So let me just quickly define this cute little tool, super dense PKE from LWE. So what is density? Density says the probability that a random string is a valid public key. And so here we're not constraining the public key space artificially. The public key space is really the space of all strings. And the density really refers to, and what do we mean by valid public key? We mean a public key for which a string for which there exists a decryption key. And this decryption key may not be of the form of an honest decryption key, but as long as it works for decryption. And this was previously unknown from LWE. There are a bunch of works from Goyal et al., Badrina Ryan et al., who construct a statistical WI from LWE, quasi-poly or sub-X LWE. And in fact, in the second work, they actually explicitly mentioned that they don't know of the existence of this superdense PKE from LWE. So by superdense PKE, we really mean that all possible strings are valid public keys. Right, let me show you how it works. It's really simple. Let's start with the dual regev encryption scheme. The dual regev encryption scheme has public keys of the form A for tall matrix A, R transpose A, where R is a short vector. So the decryption key is just R transpose -1, which is a short vector. And encrypting a bit B just adds an LWE sample to the vector 0 with the bit B in the last position times Q/2. So that's the ciphertext. To decrypt, you're just going to left multiply this ciphertext by R transpose -1. And R transpose -1 with the A matrix will cancel out to 0. Then you have short times short for R transpose -1 in a product E. And finally, you'll get R transpose 0, which is 0. And then you'll add either a large value if the bit is 1 or 0 if the bit is 0. OK. And then you round. So what makes a matrix a valid public key? Well, it's the existence of a short solution with a non-zero last coordinate. And this is certainly not true of many matrices. For example, take the all zeros matrix and large values in the very last row. So dual regev is not super dense. But there's a really simple way to make this super dense, which is instead of encrypting just one ciphertext, we're going to make a bunch of ciphertext, one ciphertext for every coordinate. And for every coordinate, we're going to place the bit B in the ith row. And just observe now that no matter what matrix A you pick, by the totality of the matrix, you know that there's some non-zero short solution. This non-zero coordinate can be in any point. And it doesn't matter which point it is because you can just pick the corresponding ciphertext and recover the message. And that gives you super density. OK, so that's it. So open questions are, can we obtain plain model non-interactive VWSS? So either in possibility or feasibility result. This would mean that you'd get something that's morally like zero knowledge without setup in the plain model. And this is related to the open standing question of plain model non-interactive witness hiding, which has been, there's been works by Kuyank et al., or I'm probably saying his name wrong, from TCC 2020, on showing that it's likely that non-interactive witness hiding exists. And yeah, this is a super interesting question. Hope more people think about it. Thank you very much.
Are there questions? Come to the microphone, please.
So I think witness hiding and witness indistinguishability are related for some types of relations. Is there anything there that you can explore, maybe?
Yeah, so witness semantic security implies witness indistinguishability. So you can show this straightforwardly. So
WH and WI, I mean.
Sorry?
WH and WI.
Yeah, WH and WI. So you can show that you can take a WI protocol and you can.
Yeah, and if the relation is not like, it's a decent relation.
If it's a decent relation, yes.
OK.
Yeah.
And there you can explore something, maybe?
Yeah, there you can explore something as well.
Does that also apply to your construction?
Not generic
framework. OK.
to WSS.
Your definitions, to the two definitions that you had on the top.
Oh, I see. No, not to my knowledge. Not to my knowledge. The problem is this verifiability property seems incomparable. Okay. Yeah.
Unless I misread, I think in your definition of witness semantic security, you impose F to be deterministic.
Yeah.
Why? Like, would something change if f could be?
Yeah, so the notion of zero knowledge already in some sense captures some sorts of randomized functionality, so it doesn't really make sense to consider randomized functionalities. And also in general, for it to be well defined, like when you do these reductive proofs, things need to be deterministic.
They need to, or is it easier?
I believe they, I want to say need to, actually.
Okay.
Yeah.
Thank you.
So I have a question regarding the two definitions that were like in the middle, right? Not the generalized one.
Yeah.
It has you had this function f, and the second definition that you were supposed to have. What was the property? Input, output, friendly, or something?
Yeah, verifiable input output.
Verifiable input, output. Exactly that one. So could you please elaborate? I think you said that this is equivalent to existence of like a witness, such that f of that is equal to y. So it seemed to me like f is supposed to be very powerful. So what exactly is what exactly the class of this function f?
Okay, good. Like, so these functions are, so for example, the identity function would give you the fact that you can't produce any witness. That's an example of a function. But why do you need this verifiability property? Actually, if you remove this verifiability property, you get something that's potentially even stronger than distributional zero knowledge. And we actually show this in the paper. This verifiability property is necessary for you to have any reductive argument. Because what ends up happening is you need to actually, for example, suppose you break this definition of witness semantic secure in one world, you recover some value y. How do you actually know that it's a function of a witness? If you can't verify this, then you can't actually distinguish between two worlds in the hybrid, the world where you can't produce it and the world where you can. So this verifiability property is necessary to know whether or not you got a good answer.
Right.
And in fact, if you remove it, we can actually come up with heuristic constructions that for which they satisfy the non-verifiable notion, but are not. But distributional zero knowledge does not even. We can show that distributional zero knowledge does not imply the non-verifiable notion generically. So it's even stronger than zero knowledge.
But what was the class of the function? So f is supposed to be like a polynomial verifier?
Yeah, so f.
Checker?
Yeah. So for v sub
model.
f, for example, could be an NP verifier.
Okay. Oh, okay. Thank you.
Yeah, so it can be any other circuit. Yeah.
Make it short, please.
Yeah.
Short. So my question is a bit philosophical. So all your notions were very non-uniform. Like
Yeah.
There's non-uniform simulation. Is there a uniform complexity possibility of these notions?
Good question. We haven't really explored that, but I'm not sure. Yeah.
Thank you.
Yeah.
Okay, thanks a lot
Yeah.
to the speaker again. Okay, the second talk is Monotone Policy Aggregate Signatures by Maya Faber-Brodsky and Alka Ray Chandri and Abhishek Jain and Omar Panas. And Maya is the speaker.
Can you hear me? Yeah. Okay, so hi, I'm Maya. I'll be talking about monotone policy aggregate signatures, and this is joint work with Arka, Abhishek, and Omar. Okay. So before I jump into monotone policies, I want to start with vanilla aggregate signatures. So here we have a group of parties, and our goal is to prove that all of them have signed some message. So we start by aggregating the parties' keys into a short group key. And later, given a signature from each one of the parties, we can merge them together into a single aggregate signature that could be verified in time that is independent of the number of parties. So aggregate signatures are great, but they're a bit limited. For example, think of some large decentralized organization. We wanted to be able to sign messages even if not all parties are in agreement, but say just a majority of them are. For this, we have the notion of threshold signatures. And in a T out of n threshold, it's enough to have signatures from at least T parties to generate an accepting threshold signature on behalf of the group. And these threshold schemes have lots of applications in areas like blockchains, distributed voting, and so on. The main drawback of threshold schemes is that virtually all constructions that we know of require some trusted setup procedure to be run in advance, generating shares of a key for each one of the parties. And in practice, this is usually implemented with some interactive protocol, which is often a real bottleneck when too many parties are involved. So in this work, we ask whether we can get the best of both worlds. So first, like in aggregate signatures, we want each party to be able to generate its own key and for any signature scheme. And second, we still want to be able to aggregate based on threshold, weighted threshold, and more general policies. And we call this notion monotone policy aggregate signatures. So as a first step, I want to ask, do these sort of dream signatures exist, or are they just too much to hope for? And for this question, it turns out that we already have some feasibility results. So we can construct these dream signatures for any monotone policy, assuming snarks for NP. Unfortunately, we don't know to construct snarks for NP from standard assumptions. And in fact, we have some strong barriers towards that. So instead, I want to ask the question, can we construct these dream signatures from standard cryptographic assumptions? So without using idealized models or full-fledged snarks. And in this work, we answer this question positively. So we show that we can construct these dream signatures for large classes of monotone policies, assuming just bargs. And compared to snarks, bargs are a much weaker primitive, and by now we have constructions of them from a variety of standard assumptions, and we can use any of them to instantiate our results. Okay, so before I tell you more about the results, I want to sort of expand on the notion of monotone policy aggregate signatures, and specifically I want to define what it means for such a scheme to be secure. So security is defined in a game, so we have some adversary, and we have a bunch of honest parties. And the adversary can sort of make queries to these parties. So it can ask any party to sign any message that it wants. It can completely corrupt a party and receive its secret key. Or it can take apart an honest party and just replace it with its own malicious party. And it can make any number of these queries, and it can do it adaptively. And finally, it outputs a message and an aggregate signature. And for security, we require that it's hard for an adversary to come up with an accepting signature unless it corrupted enough parties to be able to generate it. So for example, for a threshold, you can't come up with a threshold signature unless you queried enough parties, unless you queried at least T parties. So this is sort of the strongest security notion that you could hope for. In addition to this, we also define a weaker notion of security, where here we limit the adversary to sort of fix the corrupt and sign queries in advance, but it can still make adaptive replace queries. Okay, so that's our security notion, and next I want to tell you a bit more about the results. So for our first result, assuming batch arguments, we construct these aggregate signatures with strong security for the class of all read-once log-space monotone policies. So let me define this class. So here we start with some state of size log n, and we have this machine that reads bits one by one, each bit telling it whether the next party has signed or not, and then it takes the bit and the previous state and it outputs a new local state. And then it sort of continues reading bits one by one until finally it outputs either an accepting or a rejecting state. And this class of policies is actually quite expressive. For example, you can decide a t out of n threshold by having the state maintain a counter counting up to t. And you could generalize this to weighted threshold and many other policies. Okay, so that's our first result. For our second result, we can handle a larger class of policies. So we can handle any polynomial-sized monotone circuit. But we only achieve this weak security definition that I mentioned. Finally, I want to also mention two extensions of our result. So first, if you're willing to assume super polynomial security, you can handle higher space policies with full security. And second, we have this nice feature of a fast prover, where if you're aggregating based on threshold, the prover only has to run in time that is proportional to t and not to the number of parties n. Okay. So next, I want to tell you a bit about our techniques and how we construct these signature schemes using new types of proof systems. Okay, so our starting point is this notion of a monotone policy batch argument. Here we have some monotone function, and we have a batch of NP statements, And our goal is to prove that enough of these statements are true to satisfy this function. And again, rather than just sending a bunch of witnesses in the clear, we want to sort of merge them together into a single short proof that is basically just the length of one witness. And very recently, Brzezinski et al. Constructed these monotone policy bargs for all polynomial-sized monotone circuits, assuming LWE. Okay, so intuitively, these bargs seem like the perfect tool for application. So to aggregate signatures, we could just have the aggregator play the role of a barg prover and give a short barg proof that there exist valid signatures from enough parties in the group to satisfy the policy. Okay, so this may seem to work, but it turns out that the challenge here is proving security. So in particular, suppose we have some malicious aggregator that can break our security game. What we want to do is we want to use the barg soundness to extract forgery to the underlying signature scheme. So to extract some signature for a party that the aggregator hasn't corrupted. And note that to do this, to extract from the barg, okay, so note that sort of the statement that the aggregator is trying to prove is chosen adaptively. It can choose the keys and the message adaptively. And it turns out that getting adaptive knowledge soundness for bargs is actually, it actually implies snarks for NP, which again, we don't know to construct from standard assumptions. Fortunately, we're not back to square one just yet. And the reason is that Brzezinski et al. Do achieve some weak extraction notion for their bargs that works even in the adaptive setting. So let me define this notion. They define this notion of somewhere subset extraction. And first, let me say what a necessary subset is. So given some monotone policy, we say that a subset of inputs is necessary if any set that satisfies the policy must intersect with this necessary subset. As an example, considering a T out of n threshold policy, any set of size greater than n minus t is necessary, since any satisfying set is of size at least t and must intersect with it. So that's a necessary subset. And given this definition, I can define somewhere subset extraction. So again, we're in the setting where we have some malicious prover choosing adaptive statements. And in somewhere subset extraction, we can program the CRS on any necessary subset that we want. This CRS is going to be indistinguishable from the honest CRS, so the prover can't tell which subset we've programmed. But given an accepting proof for that CRS and the trapdoor, we can extract a witness for some instance inside of that subset. Okay, so that's the definition. And now let's see if this definition is actually enough to argue security of our construction. So again, we have some malicious aggregator, and our goal is to extract from it a signature to the underlying signature scheme. And here's the idea. The reduction is just going to program the necessary subset that contains all the honest parties in their security game. So all the parties that the adversary hasn't corrupted. And then we can use somewhere subset extraction to extract a witness for some party inside of that subset, which is going to be a forgery to the underlying signature scheme. So this reduction seems like it may work, but it turns out that there is a major problem. And the issue is that, note that the adversary can adaptively corrupt parties. And so sort of we don't know this necessary subset in advance, and we can't program it into the CRS. I do want to note that in the specific case of n out of n aggregate signatures, so vanilla aggregate signatures, Waters and Wu actually showed that somewhere extractability is enough. And the way that they did it is by just programming a random necessary subset into the CRS. And in the case of standard batch arguments, a necessary subset is just some index. So they could argue that by programming a random index, it was the correct index with probability 1 over n, and so they were able to extract a forgery with probability 1 over n. Unfortunately, this strategy doesn't extend to our case, And the reason is that for general monotone policies, there could be exponentially many necessary subsets. And this is even true for simple thresholds. And so we can't hope to just guess the right necessary subset and program it into the CRS. Okay, so sort of we're left with a state where we have monotone policy bargs, and they seem like the perfect tool, but the security definitions just don't work. And in this work, to overcome this problem, we introduced a new security definition for bargs that we call adaptive subset extraction. So here, we don't need to program any necessary subset into the CRS. Instead, we let the prover choose it adaptively, just like it chooses the corrupted parties adaptively. However, we're going to have to trade this increased adaptivity with a loss in extraction probability. So we can't hope to extract a witness at all times. We can only extract a witness with probability 1/n. And sort of you could see that this loss in extraction probability is necessary. Okay, and given this definition, we can indeed get full security for our signatures. So the previous reduction just works. Okay, so before I finish, I want to tell you about our constructions. So our first construction is for all read-once log space policies. And for this class of policies, we construct monotone policy bargs with adaptive subset extraction. And we show that this is enough to get full security for our signatures. Unfortunately, I won't have time to really go into the construction of adaptive subset extraction. So I just want to give you the main idea. And sort of the main idea is to use simulation security. So just extraction is not enough, and we need simulation security. And specifically, we're going to use this tool called the verifiable private information retrieval scheme. That essentially lets us say that if we extract a witness for some index, that witness is going to be indistinguishable from a witness taken from an accepting distribution of witnesses. So to give you a flavor of what this lets us do, if we just program a random index into the CRS, verifiable private information retrieval guarantees that the witness that we get is going to be if we do this for a threshold policy, the witness that we get is going to be accepting with probability at least T/n. And so sort of we can argue that with good probability, it's also going to be in our necessary subset. So this is the main tool that we use. And to go beyond threshold policies, we actually extend this tool of verifiable private information retrieval to a new, stronger notion of simulation security that we call composable simulation security. And we show that using this notion, we can get adaptive subset extraction for bargs. Okay, so that's our first construction. For our second construction, that I won't have time to go into, but you could find details in the paper, we introduce a new, completely different notion of extraction that we call functional subset extraction. We construct it for all polynomial-sized monotone circuits, and we show that it implies aggregate signatures with weak security. And finally, I want to leave you with an open question. So we had this notion of somewhere subset extraction for bargs. And in this work, we introduced two new and incomparable notions of extraction that we call adaptive and functional subset extraction. And they let us get different applications. And I want to ask you, what is the right security notion that we can define for monotone policy bargs? And hopefully, getting a good security notion is going to lead to even more applications. Okay, that's it. Thank you.
Questions?
No? Okay. The first construction that you have on the our contribution slide, you mentioned that the class of policies that it covers was like read-only, log-sized, right, policies. So, and you mentioned very quickly that it is generic enough to cover weighted threshold policies.
Yeah.
So could you just elaborate, give some intuition on that class of policies? So maybe yeah, it can be a bit more tangible. What can you do with that?
Yeah, sure. So let's say, so for example, to decide weighted threshold, what you can do is you can just have the state maintain the sum of all the weights that you cover so far, and then you sort of read the bits one by one, either increase the sum or not, and then finally you decide whether it's larger than the threshold or not. And in general, you could extend this to anything that you can decide with small space. And if you're willing to assume like 2 to the s security, you can extend to s space rather than log space.
Okay, so there is a decider in the end of this procedure, right? In the end of this
Yeah, in
policy,
the
you
end you
decide
take-
whether the value is in the threshold set or something
Yeah.
after you aggregate. But what was the weighted part that you mentioned? So you mean that every time you add a bit, but you can also add a bit with like a weight to the global sum?
Yeah, and
Is
weighted
that what you meant?
threshold, like you have a weight to each one of the parties.
Right, okay.
And you want the sum of the weights to be at least t.
And you can still encode that in the log space.
Yeah, assuming the weights are not too big.
Okay.
So, yeah.
Okay, thank you.
Hi. Following up on the previous question, is there an example of any interesting monotone policy outside of the thing, outside of the...
Outside of read once log space?
Yes, exactly.
I'm not sure if I have one off the top of my head, but
So that's good. Basically, you covered all of the interesting ones, right?
yeah, we have, yeah.
Okay, then thanks to the speaker again. The last talk in this session is about strong batching for non-interactive statistical zero knowledge by right? Okay,
Can you hear
by
me?
Mew and
Hi, can you hear me? Great. I'm Chang Rui. Today I'm talking about the strong batching for non-interactive statistical knowledge proof. The talk today is based on cooperation with Shafii Nasha, Ron Rosblum, and my supervisor Prisha. So zero knowledge is an amazing notion where a prover can put a verify about statement without revealing anything beyond the validity. We also can make the prover to be non-interactive. And to do this in a non-trivial sense, we need to work on the common random string model or CLS model. Specifically in this model, both the prover and verify receive the common input X and has access to the CLS string. The prover will refer to the CLS with the generate proof pi and send it to verify. Verify check the pi and decide either to accept or reject. We ask for standard completeness and soundness, meaning if it's a yes instance, then the honest prover can make a verify to accept with a high probability. But if it's a no instance, the no prover can make a verify to accept with a non-negligible probability. Lastly, we ask for the knowledge property, meaning there exists an efficient simulator that would take any yes instance and generate a distribution that would be close to the real view of the verify in the real protocol on the instance. In this study, we focus on statistical zone knowledge, meaning the distribution that simulator generates is statistically close to the real view of the verify, and also the soundness would hold for any prover. And in the rest of the talk, we would abuse the notation of a NISI to also represent a set of problems that has a non-interactive statistical zone proof or NISI protocol. So NISI protocol is for verifying one instance. What if I have a k instance to verify and want to verify to accept only if all of them are yes instance? That's the setting what we call the batching verification. As you may imagine, very naive solutions just to repeat the original protocol for k copies on this k instance. And in that case, we start from a protocol with n bit of communication. Then we get a batching protocol with a k times n bit of communication. What we're asking is whether we can do it better in terms of run complexity and communication complexity. This is because these are valuable resources in scenarios such as signature verification. So we call this non-trivial batching. Our interest is to know which class of the problem can have the non-trivial batching. So from the celebrity IP equals to P space theorem, we can indeed verify K P space statement with very little overhead. So we can indeed do non-trivial batching for all IP languages. However, the transformation will lose some good property of the original protocol that we may be interested in, such as the efficiency of the prover and the zero knowledge property. If you only care about the efficiency of prover, there's a very amazing line of work done by Rosplans and Ringo. They made doubly efficient batching for all NP language with a unique witness. There's also doubly efficient batching for all NP language with just a computational soundness based on some cryptographic assumption. In this work, we want to know whether we can do non-trivial batching for in the knowledge manner. So specifically, our main question is that suppose a problem that has a statistical knowledge proof, whether we can do non-trivial batching for this problem in zero knowledge. In previous study done by Castellassi and other amazing researchers, they've found out that for any problem that has a non-interactive statistical knowledge proof, would have an interactive statistical knowledge batching with the communication linearly additively depend on number of instance k. And in this study, we improve the result in terms of both run capacity and communication capacity. Specifically, our transformation would maintain the non-interactiveness of the original protocol, and our communication and the CLS length are both just dependent on polylog k. So the following is our main theorem. Every problem that has a non-interactive statistical knowledge proof would have a non-interactive statistical knowledge batching with the communication and the CLS length, both poly and log k. So in rest of the talk, I'll firstly give the background and the bottleneck in previous study, and then I will introduce our solution by giving the key observation and the new protocol. In the end, I'll offer a set of open questions for future. So to begin, let's first look at this one more question, what we call the permutation problem. The input to this problem is a length-preserving circuit from n bit to n bit. The yes case is when the circuit is a permutation, and no case is when the circuit is a 2 to 1, meaning every image will have at least 2 per image. And this permutation problem turns out to have a NISE protocol. Specifically, actually, the NISE protocol is quite simple. The CLS is just a random value z from 2 to n set, and the prover is asked to find the pre-image of z and send it to verify. Verify check that. We notice that the protocol achieves perfect completeness because on the yes instance, the circuit is a permutation. So any value z would have the exact one unique pre-image. So the unbounded honest prover can always make a verify to accept. It also achieves soundness because on the no instance, the circuit is 2 to 1. So with probability at least half, a random value z has no pre-image at all. So no prover can make a verify to accept. Lastly, it achieves the knowledge property because the simulator can sample random value x and output cell x together with x, which is identical to the view of the verify in the real protocol. Last but not least, we notice that the communication and the CLS length in this protocol are both just n bit, which is equal to the input-output length of the circuit, independent from the circuit size. After seeing the NISE protocol for permutation, let's do NISE batching for it. We observe that the circuits they are length preserving. That means we can compose them by connecting one's output to the next input. And by doing this for the K circuit, we get a circuit CK bar, which turns out to be a new instance of permutation problem. This is because if all the K circuits are permutation, then the CK bar will still remain to be a permutation. But as long as if one circuit is 2 to 1, then CK bar would be at least 2 to 1, because the circuit cannot resolve those collisions. So with this nice observation, we know that the prover and the verifier, they can reduce a K instance of permutation to one instance, the CK bar by themselves. And they will do that themselves and then only run one execution of NISE protocol for CK bar. Then make the communication and the CLS length both just n bit, again, just input-output length of circuit, independent from the circuit size, and also the number of instances K in this case. If we can prove that the permutation problem is NISE complete, then we're done. Because if we want to do NISE batching for all NISE problems, we can reduce those problems to this and run the protocol. However, we don't know how to show this. And in fact, there's evidence suggesting that it's unlikely. But indeed, in previous study, there was a very similar problem, what we call the opposing injectivity problem. It's indeed nearly complete. The input to this problem is a circuit from n bit to t bit, where the t is larger than n. So it's not length preserving, which will be a problem in the future. And the yes case to this problem is a circuit that is injective on all but the delta fraction inputs, while the no case is when the circuit is L21 on all but delta function input. And it's proven that this opposing injective circuit problem, or AI problem, is nearly complete for a very large range of choice parameter L and delta. This problem is essentially just to distinguish almost injective circuit from those very non-injective circuit. So for bird's eye view, we start from a k instance of a problem, and because this AI problem is nearly complete, we can reduce all of them to the k instance of AI problem or problem size. We only need to do batching for this AI problem. And take the experience I had for the permutation problem. If we can efficiently reduce k instance of AI to one instance, then we can have a similar batching protocol. To see whether we can do this, what we figure out is that the circuit, input instance circuit in this AI problem is not length preserving. So we cannot connect them directly like what we did for the permutation problem. A very natural idea is to use some good hash function to connect them. To see whether this would work, let's consider C1 and C2, they are both injective circuit, and we use some random hash function to connect them. What would happen is that the random hash function would introduce a substantial amount of collision. That is to say, if we start from a k permutation, k injective circuit, after this hash composition in the end of CK bar would be very far from injective. And that would break our promise. And indeed, in previous study, they resolved the collision through interaction round by round. And that is why the protocol was highly interactive, and also the communication was linearly dependent on number of instance k. And in this work, what we observe is that this good property, what we call the collision probability, is preserved under this hash composition, and we can use this property to make a reduction. To see why the collision probability is preserved, let's consider, take a closer look at one layer of the composition. So the collision probability, say C1 is an injective circuit, and the hash is a random hash function. So the collision probability of C1 is defined to be the probability that the two random independent inputs are mapped to the same value by C1, which is equal to 1 over 2 to n because the C1 is injective. The question is whether the collision probability of HC1 be much larger. To see this, let's firstly consider the expected collision probability of HC1 over the randomness of a hash function. By some conditional expectation, we can bound this expectation by the summation of these two terms, where the left term captures the collision probability of C1, and right term captures the probability that there is a hash function mapped to distinct input to the same value to introduce the collision, which is equal to 1 over 2 to n because the hash function is random here. So you see, actually, the expected collision probability grows very slightly. And similarly, because this hash function is at least 4-wise independent, so we can also bound the variance in the same way. And given an upper bound for both expectation and variance, we can apply the Chebyshev inequality and prove that the collision probability of HC1 would be only 2 over 2 to n larger than C1 with a 1 negligible probability. And by induction, we can show that when we compose K circuit, the collision probability of CK bar would be bounded by 2k plus 1 over 2 to n with a 1 negligible probability. And this would suggest that, in this case, CK bar would have a high collision entropy, which is defined to be minus log collision entropy of circuit. But in the other case, as long as there's a circuit that is L21, then the collision entropy would be at least L over 2 to n. Notably, the L can be much larger than K, so there's already a very big gap here. But in fact, what we can prove is something much stronger. We can even show that the collision, the support of the CK bar in this case is even small. That would suggest that the max entropy of this circuit, CK bar, would be small. So to conclude, if we start from a K-injective circuit, then CK bar has a high collision entropy. But as long as there's one circuit that is L21, then the CK bar has an even low max entropy. We're dealing with a opposing injective circuit, we may not be able to show that the CK bar has of high collision entropy. But because each of the opposing injective circuit is statistically close to exact injective circuit, in the end we can still show that the CK bar in this case would be statistically close to a circuit with a high entropy. And so to conclude, if the K instance are all yes instance of opposing injective circuit, then CK bar would be close to a circuit with a high collision entropy. But as long as there's no instance of opposing injective circuit, then CK bar would have even low max entropy. And the problem to distinguish the two cases is what we call the smooth entropy approximation, or SEA problem. It can be shown that this problem has a NISE protocol. This is because we can reduce it to another well-known NISE complete problem statistically different from uniformity. The high-level idea just use some random hash function to extract out the entropy to uniformity by level Hessian lemma. Okay, great. So by far we know that the SEA problem has a NISE protocol, and we can reduce K instance of AI problem to one instance of SEA, so we can have our batching protocol. That would be the prove and verify make the reduction to the SEA and only run one execution of SEA protocol. And notably, the SEA protocol communication cost is poly and log K, so our batching protocol's communication cost is also this. However, in this case, the CRS length would be still very long because these hash functions in the reduction, they are independent, and we sample the hash function from the CRS. To resolve this issue, in the paper, we have a de-randomization process. This portal technique is more self-involved, so we refer audience to our paper for detail. But the high-level idea is that the collision probability of a CK bar defined by the sequence on hash function can be modeled by a rate-once branching program. That allows us to use the Nissan pseudo-random generator, which can fool the rate-once branching program to sample hash function instead. And it can be proven that if we sample the hash function using PRG, the collision probability of CK bar won't change much. And moreover, the seed for the Nissan's PRG is quite the same as much as just a poly and log K. So finally, our protocol would be we sample the hash function with the PRG, and the seed is from the CRS, and make our CRS length also poly and log K. So in conclusion, our main theorem is that every problem that has a non-interactive statistical knowledge proof would have a non-interactive statistical knowledge batching with both communication and the CRS length, poly and log K. In the future, we'll have a few interesting open problems, and the most intriguing one is we want to see whether we can do non-trivial batching for the general in the knowledge for the general SDK class. And also, we want to know whether we can maintain both the proof efficiency and the knowledge property simultaneously. There was a recent work done by Caron, Rosblum, and Prushan that made progress on this direction. All right, that's all from my side. Thank you.
Are there questions? No. So, okay, then let's thank the speaker again.
Okay, thanks.
Thanks a lot.